Okay, so again, these were the forms of electrons we left off last time. This is the alpha, beta, and gamma particles we had talked about last time. And remember, the alpha particle can be denoted with alpha or 4 over 2, 4 meaning the mass, 2 would then be the number of protons, right? Or the atomic number. And He, it would have a 2 plus charge because if it's an alpha particle, it's just been created, it's been injected, and so it doesn't have time to get any electrons yet. Okay? What ends up happening is alpha particles, if they hit you, would then take electrons from you. Okay? And then you'd have helium, like a balloon. This right here is a beta particle. It can be denoted by a B-looking thing. That is beta, the Greek letter beta, capital beta. And this right here has a mass of 0, -1 charge. It's an electron. The difference between a beta particle and an electron is that a beta particle is just moving very, very fast. Okay? Otherwise, it's just an electron. Gamma particle. This is actually a form of electromagnetic radiation, or another way of saying that, it's the same sort of radiation as light is. Okay? Do you know what the largest radiation source that you encounter on any given day is? Yeah, the fluorescence lights if you're indoors, and if you're outside, the sun, of course. The sun is just a huge ball of radiation shining down on us. So you're exactly right. The fluorescent lights indoors, biggest source of radiation by far and away. It's actually a more powerful radiation source than a typical like 5G tower would be within the distance you could get to it. Now, if you were to go right up to the 5G tower and put your head in it, then you could get more. Okay. Positron, this is going to be... positron, this is going to be a positively charged electron. Okay? It's very similar to the beta particle. It just has a positive charge. Has anybody ever heard of antimatter? Yeah? Like antimatter or photon torpedoes or whatever? Huh? Yeah. So this is what they're referring to. Yeah. So positron is the electron version of antimatter. So all antimatter is just flipped charges. And so if you have a positron impact with an electron, it's going to annihilate each other and they produce energy in the form of typically gamma radiation, but usually some radio waves as well. Neutrons, you guys all know neutrons. In this case, we're talking about a neutron popping out of your nucleus and flying off somewhere. Okay? Again, it's going to be ejected at very high speeds. And so, like, these neutrons are so fast, if they hit nuclei, they can sometimes crack those nuclei open. Okay? And that's how you get most radioactive reactions, nuclear reactions happening. Neutrons have mass 1, charge 0. Anybody ever heard of a PET scan, by the way? PET scan? Yeah, some of you. Okay. So a PET scan or PET scan is actually a positron emission tomography. Anybody know why it's stupid to say PET scan or PET scan? A tomography is a type of scan. It's like saying PIN number. Do you guys know what PIN stands for? Personal identification number. So when you say PIN number, you're saying personal identification number. And so when you say PET scan, you're actually saying scan. I'm taking a positron emission scan. So next time you hear a doctor say that, you can make fun of them. Yeah. They always say it too. Always. And PIN number gets used all the time, right? They could just say CT. Yeah, They don't have to say scan for that either. So all those abbreviations, they're all types of scan at the end. So but yeah, I understand what you're saying because the English language doesn't sound right when you just do abbreviation, nothing else. Yeah, I want a pet. Doesn't sound good, right? Even though it is grammatically correct. But it's funny because they're actually going like scan all the time. Yep, scan. Alpha particles. This can be represented again, Greek letter alpha, 2 plus charge. Beta particles. And again, gamma rays. Remember that these are going to be the higher energy electromagnetic radiation than X-rays. Okay? They're very, very high energy. Whenever they hit you, they're basically going to obliterate your molecules and break them up, okay? So what you would notice is if you have any significant gamma rays hitting you, it's going to basically vaporize you. And you really don't want a lot of gamma rays hitting you. However, I'm going to say right now that you actually have gamma rays hitting you every day of your life. Okay? Small amounts of gamma rays hit you every day of your life, even if you're indoors. Okay? They're very, very high energy. But, usually it's not that big of a deal. You can think of gamma rays as kind of like, so if I had like unstable structures, right? They're eventually going to collapse, right? Everybody's okay with that? And what are they going to produce? Well, they're going to produce new structures, i.e. rubble, right? And they're going to produce sound when they collapse, right? So all the previous ones, these were the rubble of these nuclei when they collapse, okay? The gamma rays are like the sound when they collapse. Most of these nuclear reactions are going to have gamma rays, and they're going to have some radio waves that come off, okay? And those are like the sound of the energy being released, okay? And so their energy being expressed in the form of light or electromagnetic radiation. The rest of these are actually the mass and the particles being shot at. Okay, positron. This is an antimatter. So when they actually do PET scans, they actually shoot you with a beam of positrons. That's actually what that is. So they're shooting you with an antimatter beam, like some sort of science fiction show. Pew, pew, pew. And what they're doing is they're allowing those to annihilate themselves with your electrons. And what that ends up doing is it actually causes little bursts of radio waves, which they can then track down to specific three-dimensional locations. So that's kind of how a PET scan works loosely. This is a neutron being ejected in a decay. This would be a radioactive decay. These are very, very common method of radioactive decay. And you'll see in a little bit that this is actually how you can get things like nuclear chain reactions. Okay? Is, for example, if you were to take uranium and put them close enough, what would end up happening is each of the uraniums, when it decays, would shoot out 3 neutrons. And if you have another uranium that gets hit by it, it's going to shoot out 3 neutrons because its radioactive decay is going to get triggered by getting shot with a neutron. And if you have a bunch of them all packed together really close and enough to cause them to be really densely packed together, so each shot causes another one to go off, what would you call that if you did that with like gasoline? You lit one gasoline and it caused all the other gasoline to light off. It go boom. And so that's actually a nuclear weapon if you get enough uranium or plutonium, for that matter, all in a single location. Okay, that's called critical mass. If you keep that just under the threshold that can't go, parabolic in its shape, then that's a reactor, a nuclear reactor. And if you keep it so it never can go critical, then you just have a heat source that will slowly heat things, like the satellites do. So biological effects of radiation. radioactive emissions will contain a lot of energy. They will interact with atoms, whether living or not. Doesn't really matter. They react pretty much the same. However, in living organisms, that damage can get propagated, and it can be much more meaningful. Okay? Alpha and beta particles, neutrons, positrons, gamma rays, and X-rays, these are all what's called ionizing radiation. And what those mean is that they cause whatever they hit to become ions. Okay? Either positive or negative. Right? Alpha and beta particles are kind of self-explanatory because they're already charged, right? So they kind of make sense. Neutrons, on the other hand, are not charged. Neither are gamma rays and X-rays. So what happens with gamma rays and X-rays is they're so high energy, they actually cause an electron to launch out of your structure. Okay? And therefore you become ionic. The positrons, again, they're going to annihilate electrons, so you'll be down one electron, right? And you lose your electron. Your neutrons, on the other hand, have a tendency to knock things out of place. And so they hit your nuclei and they'll cause a nuclear reaction. That's a pretty major way that happens. So the loss of electrons in living cells can affect a cell's chemistry and genetic material. In humans, if we have a genetic change, there is a pretty decent chance it's going to cause cancer, assuming it's within a... so there's actually only a few locations on our chromosomes that if the genetic change happens, it'll cause cancer. And so we actually have this happen to us like dozens, if not hundreds of times a day. We have small genetic changes on our different cells due to various different chemicals and radiation. We are radioactive ourselves because potassium, actually, it can take on a fairly common radioactive element on the planet. And so we have a slightly elevated radioactivity in the surroundings. Okay. And so, like, most of these genetic changes don't really amount for anything. But if it targets the right place, it can actually cause cancer. Okay. And so it's just luck of the draw, I guess, and how well your body handles anytime those damages happen. We do have mechanisms to try to repair it, but they're not perfect. Radiation of higher energy can penetrate further into the tissues. This will affect cells located deeper in the body. Persons who work with radioactive materials will wear heavy lab coats, lab glasses, and gloves. This is to try to block some of that radiation from actually hitting them. They may also stand behind plastic or lead shields. And one of the things you're really going to see a lot of is that, realistically speaking, most of these radiations are not actually that harmful as long as they're external to you. Okay? But what happens if you accidentally breathe in some of the powder? Well, then it's not external to you, is it? Then it's internal to you. And so your damage levels goes up tremendously if you allow it inside of you. Okay? And that's actually one of the major reasons you do things like wear lab coats and lab glasses, and you oftentimes see them with some sort of breathing apparatus or breathing mask, okay, to prevent that. Now, having said that, did I tell you guys that one of the guys that invented the nuclear reactor, actually to demonstrate how harmful uranium is, swallowed a piece of uranium? No? And the people that invented the nuclear bombs used to carry the plutonium around in their pockets. And they all, not a single one, died from cancer. They all lived their normal length lives, not statistically different than the rest of the Americans at the time.
How do you eat uranium?
So, interestingly enough, uranium is not particularly toxic as long as it doesn't absorb. And pure uranium doesn't actually absorb in the body. So, it's a neutron and alpha emitter, and so it doesn't do that much damage really on the way down. As long as you don't actually digest it and incorporate it into your body, you're fine.
Try eating some uranium.
Don't do it. Now, the really, he knew what he was doing, and so he set himself up not to have troubles. Very, very pure sample of pure uranium metal that wasn't heavily oxidized into his system. Okay, if he had eaten an oxidized, heavily oxidized uranium, then he would have actually absorbed some of that uranium into his body. And so it was a risky thing, and he had to be very careful doing it. But if you just popped some of the yellow cake in your mouth, you'd have a bad day, a bad week actually, and then you wouldn't have any weeks. Because the acid would cause the uranium oxide to go into ionic uranium, which you can then digest. Well, you will spread in your blood system. You don't do anything with it, but it is toxic. It's about as toxic as lead, actually. Yeah. Which isn't that toxic. Honestly, lead's not that toxic, but still not something I would recommend eating. You can eat mercury. There's a lot of these things that you think of as harmful, then reality is only harmful in certain species. Probably the best demonstrator of this is chromium. So you need chromium in your diet, okay? That's chromium 3+. If you have chromium 6+ in your diet, even in very small amounts, you will die a horrible death. Okay? Anybody ever heard of Aaron Brockovich? Okay, a little assignment for the weekend, okay? Watch Aaron Brockovich's movie. It has Julia Roberts. It's actually a pretty good movie. It's based on a true story, though they've sensationalized it a bit in the movie. And so a company leaked hexachromium, chromium 6+, into the water of a small town. 400-something cases of various different diseases that were caused by hexachromium popped up in that town. What they did, though, is when they leaked that hexachromium into the water source, they held a meeting with the town and told them, hey, don't worry. We leaked chromium into your water source, but there's the 3+. It's good for you. You need it as a nutrient. They knew it was the 6+. They knew these people were going to have health problems and possibly die. And so they killed 400 people over the course of 20 years. And this company, the reason they did that and notified the inhabitants that they did that is there's a statute of limitations with environmental damage. They were only about 4 or 5 years away from that statute of limitations. And then somebody contacted lawyers, tried to get a lawyer to take this on. Erin Brockovich was a paralegal for a lawyer. And she went, there's something to this. And she went ahead and researched it and found out that there's 2 different types of chromium. Hexachromium's toxic. And they were able to trace this and find records that these people knew and everything. They took it to court. They won, sued the company. That lawyer, by the way, about 2 years ago, he was arrested because I guess later cases he had embezzled money. Yeah. So you can be a hero one day and a villain the next, apparently. But yeah. You could actually. I wouldn't recommend it. But no, if you know enough chemistry, there's probably non-toxic versions of every element. You just have to get the right, get an insoluble version of them, and they'll just pass through and they won't do anything. But you got to be careful because you have an acidic and basic environment in your body. Okay? So that's where people screw up. That's where things go bad. Okay. So people who routinely work with radioactive materials or X-rays usually wear a film badge to monitor their total exposure. It's literally just a piece of film and a little badge that's covered with laminate, essentially. And you can see the badge. I will note that those badges are only good for a limited period of time. If you are one of these people and you work around, make sure you change your badge out regularly. Okay? It's something that people don't do. Like they'll work in hospitals around the radioactive elements and they just get lazy and stop changing their badges. And then what happens is the badge just goes color one day. like really deep color. Oh my God, I just absorbed tons of radiation. And what it is previously, if you go past the date, the badge will either never turn color or it'll just turn all at once. Okay? And you'll never know which. So it doesn't do its job anymore. So this right here is alpha radiation. If you were to just take your hand and put it in front of an alpha beam, radiation beam, it would block the alpha particles. I wouldn't do it, like you'll have a little bit of warming on your hand, but that's about it. Okay? Most alpha particle beams are not going to particularly harm you that much. They will be causing some reactions with your skin, but you have like 7 layers of dead skin on you anyways, so it doesn't really matter. Beta particles can get blocked by an aluminum sheet very easy. Even enough sheets of paper would do it, really. Like a piece of board would do it. Paper will block alpha particles, by the way. Lab coats block it, everything else. Gamma radiation will penetrate through aluminum. It'll penetrate through your hand, your body. What the heck? And that is really... And you'll need a sheet of fairly thick lead to block gamma radiation, okay? Neutrons. This is going to be where you need like multiple sheets of lead or a very, very thick concrete wall. And those will block neutrons. Those will also block gamma rays. So that's why typically you see a facility that's going to handle this stuff. It'll have like thick walls of concrete with usually some steel plates in there, interspace. And if they're really concerned, they might put a lead coating in there as well. But yeah. Now there are higher energy particles. There's cosmic particles, which are essentially usually like neutrons that are just going incredibly fast and were ejected by things like supernovas and stuff. Those are constantly passing through the whole planet. Okay, a fair amount of them get blocked and dropped off from planet, but some of them pass all the way through. So, all right, this is the different protective shielding. This is tissue penetrations, and this right here is your travel distance. Alpha particles usually don't last very long, and beta particles usually don't last more than a couple meters. So realistically speaking, unless you're right up against your radiation source, these are not things you have to worry about usually. Okay. Neutrons can go incredible distances, as you probably figured out from me saying, like, if they're shot up by a supernova, they can pass through a planet. They can actually go the distance. So how much radiation exposure is too much? Okay, so we need to talk about some units. There's the sievert, which is SV. This is the SI unit of radiation here. This is actually the measure of the effect of the biological damage from that radiation. Your average dose in a year would be 6.2 millisieverts. So milli and sievert. And so you have a pretty constant baseline that you have throughout the year. If you're talking about something like an X-ray, that's going to be a couple months of radiation, your normal baseline radiation. Keep in mind that it depends on where you live of how much radiation you're going to get a year. Okay. 1 millirem is going to be equal to 100,000 sieverts. So we are exposed to low levels of ionizing radiation every day. We have cosmic rays from outer space. We have radon gas. Does anybody know what radon gas is? No? What if I told you Tennessee is a radon gas area? Okay, so anybody know what causes the planet to be... Okay, everybody's aware the planet is hotter towards the core, right? It gets very hot when you get to the core. Okay. All right, so what causes that heat? Where's that heat coming from? What in the core, though? Okay, so it's radiation. So a lot of the radioactive elements are in the core, and so when they break down, decay, they release heat, right? And the convection currents within the core help to maintain that heat. And so it very efficiently traps that heat, and that causes the core to heat up over time, and it's become very hot because of this. Okay. Now, when things break down radioactively, they're going to create what's called daughter ions. And so one of the common daughter ions that we have to deal with is radon. It's a fairly common daughter ion. It's something that's created every time things are above it on the periodic table or broken down. And radon is actually a gas. And so what ends up happening is this radon gas. Jeez, what is wrong with this thing? This radon gas is a gas, right? So it's in the core. It's surrounded by rocks. Some of them are porous. And this radon gas is going to end up being released from the core. It's going to come up through the soil, and it comes up through the ground. Radon gas is still radioactive if you look on your periodic table. And so if you were to build a basement in Tennessee, what you would end up finding out is unless you put fans to specifically manage this, you're going to build up radon gas, and you'll actually have higher rates of cancer. Okay? And as far as I can tell, there is no rules that you have to disclose, test for radon gas when you sell your house. Because I've never seen it done. But I haven't seen many basements in Tennessee either, so maybe there is. Anyways, most radon states that have radon gas seeping out of them have rules that you have to test for radon gas when you sell your house. So, anyways, keep that in mind if you have a basement. You can get a radon test at Walmart for $40. You can test for radon gas. If you don't know, if your parents don't know if it's been tested or not, you might want to do that because if it's not managed properly, it can cause cancer. Anyways. So there are, of course, other naturally occurring radioactive elements. A large amount of the radioactive elements is actually created in the atmosphere, up on the upper layers of the atmosphere. You have very high energy particles that enter the atmosphere from space, and these will cause radioactive nuclear reactions that are going to actually cause radioactive elements to be developed. Okay. And so there's a constant stream of radioactive elements that are created all the time. Human exposure to radiation has actually increased about 40% since the 1980s. This is mainly due to an increased use of radiation in medical procedures. Very little of this is actually contamination. However, interestingly enough, NASA accidentally increased the radiation of the planet. They tried to launch a probe, and they blew it up in the atmosphere and released a bunch of uranium into the atmosphere. So they're actually Fukushima and them are the two largest releases of radiation on history. So radiation sickness, the effects of radiation exposure are going to be dependent on both time and dose. One of the things you want to keep in mind is that if you have dose of radiation but stretched out over 10 years, it's just not as much of a deal if it's a small dose, okay? If you have a larger dose stretched out over 10 years, it's going to be very damaging, okay? It's kind of like, has anybody played with flames ever? Played with fire? Even though your parents told you not to? Okay. Yeah, you've seen the people that put their hands over the fire or through the fire? Okay. So if you have a very hot fire, right, you put your hand in there and hold it there, you're causing damage, right? But what happens if you just pass it through really fast? Yeah, almost nothing, right? So again, if you have less time, you can limit the amount of damage, okay? So very, very dependent on time and the amount of radiation. So long-term exposure to relatively low levels of radiation is not as life-threatening as short-term intense dosages of radiation typically. Intense short-term dosages will swiftly destroy tissues in the exposed area. Cell types that are rapidly dividing are going to be killed off more quickly than others. And so there is a major difference in the susceptibility of your cells. Okay, so for example, everybody's probably heard of cancers of the bone marrow, right? And that's because they're very quick dividing, and they're very important in what they do when they divide. Okay? And so bone marrow is pretty susceptible to radiation, right? Whereas stable organs are usually less susceptible to radiation. They don't really divide as often. This right here is going to be exposures in millirems. So typically 5,000 to 20,000 cannot be detected. 20,000 to 50,000, you have a temporary decrease in white blood cells. 50,000 to 100,000 is mild radiation sickness. You have a large decrease in your white blood cell. You have nausea, vomiting. This is where we usually start calling this radiation sickness. Okay. 100,000, 200,000, this is light radiation poisoning. You have delayed appearance of appetite loss, nausea, diarrhea, hair loss, spontaneous abortion in pregnant women. And typically you can recover within 3 months, but you're going to be in for a recovery period. Okay? And you'll have 3 months of effects, usually. 200,000 to 300,000, this would be moderate radiation poisoning. This is hair loss, fatigue, general illness. Permanent sterility is possible. Recovery is going to take several months, and you probably are going to have long-term effects. Okay? Come on. Huh? I'm sorry? Shoot. Okay, 300,000 to 400,000. Does anybody know what an LD50 is? It stands for lethal dose in 50% of the population exposed. Okay? So in 50% of the people that would have this dose right here, they would just die. And the other 50% will survive. So within 30 days, half the population exposed to this level of radiation will die. Okay? And above this, that LD50 just becomes like an LD75, LD85, on and on. Okay? And you just start killing people faster and more often. Okay, does anybody have any questions about that so far? All right. By the way, what did you notice about down here? That starts at 5,000, right? Okay, so there really is actually a dosage radiation every time they've studied it. There's no negative effects to having that lower limit of dose. You can give that lower limit of dose all the time, every day, all the time, and it has no negative effects. In fact, when they last studied it, it had a slight positive correlation, but that could have just been statistically irrelevant. Which, that would be something, right? There's a certain amount of radiation you're supposed to have. That'll be weird. But anyways, do you guys know what the prevailing policy in the United States has been for over 50 years? Okay, let's say that somebody accidentally drops uranium off on a truck. Okay, so a truck's coming by, gets into an accident, there's a small release of uranium, and now they have to clean up the area. Okay, within that affected area, do you know what level of radiation is considered acceptable? 0. They have a 0 radiation acceptability. Okay? It's no limit, no radiation limit. So technically, by U.S. law, do you know what they should contain? Throw in the giant concrete bunkers to let it deplete its radioactivity? Us. We're radioactive. We would be considered radioactive waste by U.S. law anytime that there's a radiation leak. So the current law was made after the fears of 3 Mile Island, and it's slowly changing, and hopefully they'll be able to get it fixed, but right now it is insane because there very much is a lower limit to the radiation level that is actually meaningful and would hurt anybody. We're constantly being exposed to radiation every day by the sun, right? So during a radiation cleanup, the sun is contaminant. Crazy. So how is a nuclear decay equation written? This right here is a nuclear decay. Right here, notice we have the reactant. In the case of a nuclear reaction, though, what we're going to see is that we're really concentrating on these two numbers here. Can everybody see it okay? That's what we're really concentrating on. We're concentrating on the atomic mass, and we're concentrating on the atomic number here, i.e. the number of protons and neutrons. Okay? The symbols are actually somewhat of an afterthought. Can anybody tell me why that would be? If you have the atomic number, does it really matter? No. So, as long as you have the atomic number, you can always figure out the symbol, right? Okay, so this is uranium-238. This is the atomic number for uranium. It's going to go to our products. What always has to be equal on both sides of the reaction? The mass and charge, doesn't it? Okay. And so what you'll see here is 238 on this side. Over here, these have to add to 238, don't they? Okay. Our atomic number on this side is 92. What has to be true about the other side then? It has to add up to 92, doesn't it? Yep. Now keep in mind, you can have negative charges, right? Which would be electrons. As long as they add up to the same numbers on both sides, you're good to go. Okay, and this is thorium, by the way, in case you're wondering. That's an alpha particle. Does anybody have any questions about that so far? Okay. And so that's a decay. That's how you write a decay. Notice it just is what I said, broken into steps here. This is a beta decay and positron decays. In a beta decay, a high energy electron will be emitted from the nucleus, and a neutron is going to become a proton. And you'll note that if you just follow along with making sure these numbers here match up every time, you'll actually get that every time. It's not possible to get wrong. Okay? So that's actually what a beta decay is, and that's why that's happening, is you have a neutron, it loses a negative charge, and that makes it positive. And so you get a proton from that. And in that process, it's going to shoot out a very fast-moving electron, and that's a beta decay. Now, a positron is actually the same thing, but in the opposite direction for charge. Okay? And so you would have a proton, it shoots out a positive charge, becomes a neutron. Okay? Gamma decays. Realistically, these are just an energy release only. You'll have no change in the mass or charge of things. Okay? They usually accompany other processes where they're having to release the energy. It's really just the nucleus being in the wrong structure and settling down. So a isotope that's a pure gamma emitter will not change the atomic numbers, atomic masses upon decay, because you're just releasing energy. And that's how this is actually denoted. This M here just is saying that we have that extra energy there in that structure. And it would actually be a little mass, by the way. It's just such a small amount of mass, it doesn't have a whole number. Okay? It'd be a very small amount of mass. So by emitting that gamma ray, the element's going to become more stable. And this is the equation of emitting a gamma ray. Notice these numbers don't change here. Okay? Because that's 0, 0, right? See how you can just add everything? You're always going to get your answers. Like if you didn't know this is a gamma, you can just go 99 versus 99, 43 versus 43. Well, it has to be 0, 0, right? So it's gamma. Okay, how do we produce radioactive isotopes? So we don't always find the radioactive isotopes we want. For example, if you're going to try to label something with iodine, radioactive iodine, so you can find out if there's a tumor in that person's brain, then you're going to end up needing to produce radioactive iodine. And so how you produce radioactive elements is you take the element, you put it in front of a neutron emitter typically, and how you do that is you take a lead block and you drill a hole into it, so there's a little pathway for the neutrons to shoot. Okay, and then you line up the element you want to make into the new element. You want to do the nuclear change to, and you line that pathway up and have it hit it. Okay, you'll have to do it really close, and what will happen is the neutrons will hit that element that you're targeting, and they'll cause a nuclear transformation. In this case right here, notice that we're taking 98, molybdenum-98, and we're shooting it with a neutron. The neutron is hitting the nucleus and actually getting incorporated in its structure, giving us MO99, right? Can everybody see it okay? Now, oftentimes what ends up happening is when you shoot things like this resulting nucleus can end up being not stable anymore, okay? And then this thing falls apart to something else. So they have pretty well documented pathways to make different elements using this. And that's how they, have you guys ever seen the radiation ward at a hospital? No? Typically in the basement. And it has a little radiation sign out on the front door area. I think I already mentioned this before. For some reason I always end up in it. I don't know why. They just let me like wander in. But for whatever reason, that's actually what they do at the larger hospitals. They'll do this process right here so that they can produce the different elements they need for tests at the hospital. Okay. Now note that in this reaction, we have two things on the reaction side, right? And then only one thing on the product side. So this is actually producing radioactive decay, or we have a nuclear transformation or nuclear reaction happening. Now this works here because we have fast-moving alpha particles or neutrons coming in. If you were to just introduce a neutron or alpha particle and it is not moving fast, it would not actually do a nuclear transformation, okay? You wouldn't get a nuclear reaction if this was just a standing still neutron, right? What makes this work is that when you have a nuclear decay that produces a neutron, it's moving at such fast speeds that it's going to be fractions of the speed of light. And so when it slams in there, it has a tremendous amount of energy. Okay. So let's talk about radioactivity units. You guys may actually recognize some of these. So the amount of radioactivity present in a given isotope is going to be measured using the number of radioactive emissions, or disintegrations is what they're typically called. So how many disintegrations happens in any given amount of time, that's going to occur in a second. The unit for measuring disintegrations per second is actually the Curie, and that's CI. This is named after the Polish scientist Marie Curie that studied radioactivity in France at the turn of the 20th century alongside Henry Becquerel. She actually used to, originally in her early career, her husband and her studied together. Her husband, though, died later on, and she was studied by herself and with Henry Becquerel in collaboration sometimes. So kind of an interesting character, actually, if you ever want a interesting biography to read. The SI unit for measuring disintegrations is actually called the Becquerel. This is actually referred to after Henry Becquerel, and these two were contemporaries. They did a lot of the early days of radiation, okay, and radioactivity. The activity of an isotope is going to define how quickly or slowly it emits radiation. These are measures of activity, and so it's literally how radioactive it is, and that's called activity. All right, and so these right here are the different units we've talked about so far, and they're a relationship to the other units. So a becquerel is 1 disintegration per second. A Curie is 3.7 times 10 to the 10th disintegrations per second. A millicurie is 1,000 millicurie to a Curie, and a microcurie is 1 million. Okay, let's talk about half-lives. These are oftentimes going to be talked about in terms of half-lives, of how radioactive something is, which is how long that substance takes to break down halfway. Okay? So for half of your substance to break down. Now, half-lives can be stacked, right? So if you have 2 half-lives, how much of that substance do you have remaining? Well, you halved once, right? Then you halved it again. That'd be a quarter, right? Okay. So every radioactive isotope emits radiation at different rates. Unstable isotopes emit radiation more rapidly. The less stable it is, the faster it is going to emit radiation. The rate of decay is measured as the half-life. That's going to, again, be the time it takes for 50% of the atoms in a sample to decay. By the way, the current nuclear clock is based on half-lives. Okay? Though there is a new one that's being tested right now, and I don't believe has been implemented yet. That'll be based on a quantum principle. But these are used a lot of the time to measure how long something takes because they're very, very consistent. Okay, this is going to be the physical half-life. Is another word for it. The rate of elimination from the body would be the biological half-life. These are going to be different numbers to some degree because the physical half-life is just going to be how fast it breaks down due to radioactive decay. The biological half-life will have the physical half-life plus how quickly you excrete it from your body. Okay? So like if it's water soluble, you're going to get rid of it really fast because you'll urinate it out. Right? Everybody knows you get rid of anything water soluble in your body usually every about 2 to 3 days. Okay. That's why you need vitamin C all the time. That's why your parents are always going, take your vitamin C, drink your orange juice. Stuff like that. Okay? Hopefully. So the biological half-life is going to shorten the physical half-life. This is going to lead to an effective half-life for medical isotopes. And this is actually what they're typically monitoring whenever they give you these medical isotopes is they can test you within the next 12 hours, let's say, or 4 hours. Okay? And they actually usually have to make those isotopes within a given time as well because the physical half-life will break them down over time as well, right? And so that's why they actually usually have to freshly make any radioactive isotopes they're going to use in testing within like a 38 to usually 2 to 3 day period. Okay. Decay is going to be measured on a Geiger counter typically. This is going to measure the radiation release from the radioactive sample. These are some different half-lives. Everybody knows what a Geiger counter is, right? No? Okay. Have you guys ever seen a movie where they're talking about like a nuclear bomb or radiation or something? And they have like this little box with like a little wand. And it goes tick, 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 and it goes faster. That's a Geiger counter. Okay? Geiger counters nowadays are a little bit difficult to talk about because there's actually multiple different types of Geiger counters now. But what they used to be is that little rod has essentially a plate over it that allows particles through. And when those ionizing particles go through, they're going to ionize the stuff inside. And those are going to cause pops on a speaker. And it's going to cause a little dial in it to go up or down, depending. Okay? Half-lives again. Natural isotopes have very long half-lives. That's why they're natural isotopes, because they exist long enough that we can actually find them. Okay? Radioactive isotopes used in medicine typically have a very short half-life for 2 reasons. Number one, if it's a short half-life, you only get a brief exposure. We don't have to worry about it sticking around, building up, and causing problems. Number two, we want enough that we can actually see it, right? So you wouldn't want almost no light. You'd want enough light you could see, right? And so we need something a little bit more intense than we typically find in nature. So the radioactivity is quickly eliminated in these medical short half-life compounds. Here we see some different radioactive isotopes that are naturally occurring. Hydrogen-3, this is tritium. Has anybody ever heard of tritium before? No? Oh, that's too bad. This is like what they want to harvest on the moon, so we can do tritium hydrogen reactors to power like more space exploration and stuff. Anyways, physical half-life of 12.3 years. Usually the only reason we find this one is because hydrogen gets hit by some cosmic particles and such, and gets changed into hydrogen-3, hydrogen with a mass of 3, which is then radioactive. This one has a fairly short half-life as it comes. Carbon-14. You guys have heard of carbon-14 dating or carbon dating, right? Okay. They're monitoring carbon-14. Okay. And this is why it really only works well for things that are like thousands of years old, right? Things that are hundreds of years old, it doesn't work quite as well. And things that are only decades, it doesn't work that right. Okay. An interesting little side note to this is we've changed the baseline over the last 40 years of what carbon-14 dating does. Because the amount of carbon that is non-radioactive in the atmosphere now is much higher. Because we burned all this fossil fuel. Okay? Oh, come on. What in the hell? That is just not working. Okay. Radium-226, notice the half-life is 1,600 years. Uranium-238, this is the one we find quite a bit of, and that's because it has a half-life of 4.5 billion years, right? And so it builds up, it's built up enough, and there's still enough left of it that we still find quite a bit of it, okay? In terms of these ones right here, by the way, we find radium because this is breaking down. We find carbon-14 because it actually gets made up in the atmosphere by a nuclear transformation from cosmic particles coming into the atmosphere. Okay, these half-lives are too short that we'd find large quantities of them if they're not freshly made all the time. This is the radioisotopes used in medicine. Notice these half-lives are in like a month is a long time for this. Okay, typically they're going to be half-lives that are in the hours, right? And so these are the effective half-lives if you put them inside someone. Notice that there's actually quite a bit of difference here on some of these. Some of these you excrete quite quickly, actually. Anybody have any questions about those so far? Okay. All right, so let's talk about using half-life in equations. So step 1 is determining the total number of half-lives. Step 2 is the amount of isotope remaining. Another way to solve this is to use this equation, but honestly speaking, I usually find people struggle when they use the equation and do it much easier if they just do it logically. Okay? So the equation would be the isotope remain is equal to 1/2 to the power of the starting amount. Now, this equation, what does it actually say? So let's say I have a starting isotope of 1 gram, and I go through 1 half-life. How much do I have left? 1/2 gram, right? I go through 2 half-lives. How much do I have left? 1/4 gram, right? I go through 3 half-lives. How much do I have left? 1/8 gram, right? See how I'm just doubling that bottom number every time? Okay, that's all that says. Because let's say we put a 2 in here. 1 to the power of 2 is 1. 2 to the power of 2 is 4, right? So 1/4. Let's try it out. Okay, so phosphorus 32, this is a radioisotope used in leukemia treatment, therapy, has a half-life of about 14 days. Approximately what percentage of a sample remains after 8 weeks? So go ahead and try that out. Try to calculate your answer. That way you can see how far you can get it and what parts you get stuck on. And then I will work it from here. I'll note there's two different ways you can approach this. You can approach this logically, which is how many half-lives, or you can approach this through using dimensional analysis and math. Okay? They both will work quite well, actually. Let's go ahead and start moving forward. All right, so every problem all the time. What do I have? What do I need? How do I get there, right? Okay, so what do I have in this problem? Phosphorus 32, but realistically speaking, we don't actually care what our isotope is doing. What we really care about here is we have 100% knowing. So we start off with 100%. We want to be in percentage, and we start with our full sample. Okay. So we're starting at 100%, and then we have two items that are very important for us here, right? We have 14 days, which is our half-life. And then we are going to want this at 8 weeks, aren't we? Okay. And so the next thing is, what do we want? Well, we want the approximate percentage, don't we? So at the end of this, what is our approximate percentage going to be? Okay. Okay. So the next thing we need to do is we need to figure out, well, how many 14-day periods happen in 8 weeks? Got it. Yeah. Yeah. So we take the 8 times 7, right? Or another way of saying that is we divide 8 by 2. And that would be 2 weeks right here, right? See that we can actually do this logically or mathematically, can't we? Okay, and so we've done 4 half-lives, haven't we? All right. Now, again, you can do it with the equation, or you can do it logically. Okay. If I'm going to have something 4 times, well, I have 100%. Half of 100 is 50. Half of that, 25. Half of that. And then half of that one, right? Yeah. I'd use a calculator at that point because, yeah, it's a pain, right? Why bother? Oh, man, this is a pain in the butt, isn't it? Okay, mathematically, it looks like this. So again, it would be 100% times 1/2 to the 4th power, right? Or another way of saying that is 1/2 times 1/2 times 1/2 times 1/2, right? If you wanted to, instead of doing it halves each time, you could have also just done 2 times 2 times 2 times 2, figured out that number, then 1 over that number, right? Which is 1/16. And so what we end up with is we'll have approximately 6.25%. It's possible we will be a little bit off of that, but it's going to be pretty close. Did that make sense to everybody? Okay. These really are actually not hard problems. It's kind of like once you get the trick down and you understand it like once or twice, they're all easy problems. But until you get that trick down, it's going to be mind-bending. All right, so iodine 131, you guys can go ahead and read that, please. All right, so go ahead and work on it. This is really just the same problem, right? So just slightly different numbers in it. So please make sure you work through it, and hopefully everybody can get it. If you can't, that's okay. That's why you're students and you're here to learn. I'm going to start moving forward. Okay, so again, what do I have? What do I need? How do I get there, right? And so, yeah, I do have iodine 131, but realistically for these problems, as long as it gives you the half-life, you don't have to look it up. You don't really care. Like, yeah, it is important, but not going to affect your math. And so we have half-life, it's 8 days. So that's important information. And so what fraction? So we don't have to do any percentage, do we? We can just do out of 1, meaning we don't have to do anything extra. Okay. And that's going to remain after 8 days. I'm sorry, 20 days. Okay. And so this one, we got to do a little bit more work. So we have to figure out how many half-lives have passed, right? Okay. So how can we figure out how many half-lives have passed? You got it. You got it. Yeah, so we have 20 divided by 8, right? And that's going to give us the number of half-lives that passed. Okay? And that would be 8, 16, then we have 4 remaining, right? 2.5, right? Okay, and so we put that up in the power, so 0.5 times to the power of 2.5, and that's going to give us 0.177, and we're done, because it would just be times 1, right? Okay. Any questions? Okay. So, how long would it take for 85% of P32, P32 to decay? The half-life here, see this time 1/2? Time for 1/2 of it to decay, half-life, equals 14 days. So we're just doing this backwards now, aren't we? Okay. So again, you can do this logically or you can do it mathematically. I'm going to end up showing you mathematically because it's a little easier for me to have it, up there. But I'll also talk a bit about logically. So again, try it out. Don't forget to actually read it carefully, because 85% of it is what? Decayed, right? Very easy place to get off track. Okay, I'll go ahead and move forward. Again, what do we have? What do we want? How do we get there, right? So what do we have? Well, 85% of it is decayed. So that means at the end of this, we're 15%, aren't we? Yeah, exactly. I saw a bunch of you were like saying it to me slowly. And we have our half-life, don't we? So for every halving, that was 14 days, wasn't it? So what we have to figure out is we just need to manipulate this equation backwards, don't we? So we go, instead of figuring out how much is left, have how much is left, and we need to figure out n, the number of half-lives that passed. Okay? Okay, and so let's go ahead, and this is how you do it mathematically, and this is where I'm going to start, okay? So mathematically, we have fraction that remains equals, we went ahead and changed percentage into a fraction. Can everybody see it okay? That's 15% in fractional form, right? Or decimal form. Okay, and that's equal to 1/2 to the n power. And we need to figure this number out, right? Okay, so once we have this right here, what we do is we take the log of both sides. And so the log of 0.15, that's this number down here actually, and we take the log of 1/2 to the n power. Now when you take the log of something with a power, this power actually comes down in front of the log. Everybody see it okay? Okay, and we'll be left with the log of whatever was below that power, okay? That the power was going on. Okay, and so we'll have log of 1/2, log of 0.15 here. We use our calculator. I'd highly recommend your calculator. And we figure out, well, log of 0.15 is negative 0.824. Log of 0.5 is this number here, which is negative 0.301. We divide this number over. I'm going to go ahead and move that over here because that'll make life a little easier, okay? Okay, so n equals this negative 0.824 divided by negative 0.301, and that's 2.74 half-lives. Now, what if I have a multiple choice question, by the way? Do I have to know the exact number of half-lives? No, I just need to know approximately what that number would be, right? Okay. Okay. And so, if I half 100%, what do I get? 50, right? If I half 50, what do I get? 25. 25 is still larger than 15, isn't it? Okay. And so I have to half it part of another one, but not the full one, do I? Because the full one would have given me 12, right? And that's smaller than my 15. Okay? So I'm somewhere part of the way through 2 and 3, aren't I? Most of the way to 3. Okay? So if I ever have to do this on a test and I have multiple choice question, that's all I need to get, isn't it? The option that's mostly close to 3 but not 3 is the right one. Okay? That's it. So logically, you can actually work these out very quickly in your head. By the way, if you're ever going to take the MCAT, you need to figure that out. Okay? Because they don't allow calculators on it. So once I have this 2.74 half-lives, I multiply that by 14 days, and that gives me 38 days, and that's my answer for this question, right? Okay. Let's go ahead and finish this off. We have the nuclear radiation. Can be high energy particles for high energy rays. Some of the radioisotopes of elements are going to be useful in medical imaging. This is actually what we're seeing right here, because what they'll do is they'll concentrate in particular body tissues. So once you feed that person that element, after so many hours, your body's going to start uptaking that element. Now, certain elements concentrate in certain parts. For example, your thyroid has a tendency to concentrate iodine. I don't know if you guys know what thyroid is, but it's an organ, okay? Anyways, so like if you wanted to visualize the thyroid, you could use iodine. Cancer cells, for example, are going to uptake different isotopes differently than normal cells. And so, for example, you can feed radioactively labeled glucose, and then cancer cells will take up the glucose much faster, okay? And so you can then image it, and you can see, based off the radioactive decay, releasing the radio waves and the gamma rays, depending on which one you're looking for, where those radioactive elements have been concentrated. And so, for example, we're seeing it right here. Kind of cool, right? Okay. This can be done on photographic plates, by the way. That's how they used to do it way back in the day. They don't do it on photographic plates, obviously, anymore. What they have is basically cameras, but flattish and tuned to pick up specific types of electromagnetic radiation. And they basically scan around you with those. Okay? And that's typically how that works. If you do it with multiple cameras at once, you can actually get three-dimensional structures. Typically, you need 3 detectors moving around, but you can do it with 2 if you're fast enough. It kind of depends on the instrument, how the instrument's made. Now, it's very important to expose patients to the smallest amount of doses of radiation for the shortest amounts of time. If you just kept feeding people radioactive materials all the time, you'd make your own problems, right? By the way, that's actually one way of doing chemotherapy, is feeding people radioactive materials that concentrate in the cancer cells. Yeah. So, 2 main uses of medical isotopes, radioisotopes, is diagnosing disease states, and you can also therapeutically treat diseased tissues. This one's a little bit more complicated than what I had talked about just a little while ago. I mostly was talking about diagnosing disease states. When you're diagnosing a disease state, a minimum amount of radioisotope is going to have a short half-life, so you have a very intense signal, and this is going to be called a tracer. Typically, this is actually attached to something else. Like I had mentioned for cancer, you can give somebody a glucose with a fluorine attached to it that's radioactive. Okay? And that'll be a radioactive glucose that can be uptaken by the cancer. Right? But it can also just purely be iodine that's radioactive. That's also a way of doing it. Technetium 99M. This can be used to diagnose proper blood flow through the lungs, and that's actually where we're seeing up here. You could see it looked a little bit like lungs, right? This is another example. This is actually the technetium lungs on photographic plates, in case you're wondering. And so these are normal lungs right here. This right here, see how they have cold spots in them? Right there. And so there's issues with their lungs right there, isn't there? They don't look like normal. So if there's a non-functioning area in the lungs, the tracer will not be distributed in that area. It'll show up as a cold spot, and that's because blood isn't flowing in that area, right? Or it will flow less in that area. Again, it would still be a cold spot, just a little bit warmer. Unusually high areas of activity, like areas which have blood is being detained too long in the lungs, will show up as hot spots. So, for example, they would have these very, very dark shadings as hot spots. Okay. Now, areas with rapidly dividing cancer cells will also retain extra tracer, and these can oftentimes be shown up as hot spots. Typically, what you would see is you would see like a grouping that stands out from the rest of the area in a cancer, okay? Because you'll have like a part of it that's uptaking a lot more than the rest. And so it'll show up as little dots. Okay. Now, you can also use radioisotopes to therapeutically destroy diseases or cancerous tissues. Thyroid cancer is probably the best example of this. It's a little challenging, and it really requires some very careful maneuvering because, like, you are putting radioactive material in somebody that can be uptaken. Iodine 131, this is a beta emitter. What you do is you administrate it in a dose. It's going to be 1,000 times higher than that of the tracer dose that you'd use to detect the disease. The thyroid cancer is going to greatly uptake this, far more than a normal thyroid would. And so that radioactive material in that thyroid cancer is going to cause it to die, and then it's going to release it, and your body will remove it. Now, you will get sick probably from this, okay? Most cancer treatments target both you and the cancer, and will hurt you and the cancer, hopefully the cancer faster, okay? Now, cells that are rapidly dividing are far more susceptible to ionizing radiation because their genetic material is exposed more often during cell division, and it's needed more often during cell division. And so, for example, cancer is rapidly dividing. That's the problem with it, right? And so it will damage the cancer far faster than it damages you in this case. That's why this is one of the more successful therapeutic radiation methods. Now, there is external beam radiation therapy. This is gamma radiation. It's generated from cobalt-60. This can actually be used on, like, have you ever heard of irradiated fruit? That's the fruit you buy from the supermarket. It does a very similar process. It's gamma irradiated to kill off all the cells on it. Okay. Anyways, so cobalt-60, they aim a gamma beam from cobalt-60 at where your tumor is. Usually they do 3 of these so they can line them up into a high-intensity spot. And they're trying to destroy the tissue at that one spot. Okay, it's how they oftentimes will go for like brain tumors. Brachytherapy, this is small titanium seeds containing radioisotopes are implanted in a tumor. And so they literally like put this little rod in you right at that tumor spot. And that rod is going to radioactively kill the tumor. and then they take it out of you once the tumor's dead. This is positron emission tomography. Again, PET scans. These are going to be used to identify functional abnormalities in organs and tissue. So fluorine 18 is going to be present in one of the tracers used for PET scans. It has a half-life of 110 minutes. The fluorine isotope is going to emit a positron as it decays to oxygen 18. That positron comes in contact with electrons. It's going to cause little bursts of gamma radiation whenever it does that. And so these bursts of gamma radiation can then be detected by the detector. And if you do that in a three-dimensional, 3 cameras looking at the same time with the proper calculations, you can make a 3D map of those bursts. This type of scan is very commonly used for the brain, actually, because your brain has to use lots and lots of glucose that can be fluorine labeled. So it's very convenient for that. This right here is your study guide. That's it for that. I guess we'll just call that a day. Huh. We are. So you'll meet me at the lab this Friday. We're going to do the check-in procedures and talk about what the class entails, etc. We'll also do a review at the back half of the lab. That is essentially what you should have learned from algebra, what you should have learned from your previous sciences back in middle school. Yeah. And I know the laugh is why we're having the review, right? Some of you it will be review, some of you it will not be, and we'll get to
I got lost.
Yeah.
Our building is in and the best parking lot to go to, but
Yes. So
probably try to get a parking pass.
the lab is in main hall. It's the hall with the big clock tower. Okay. And so if you just go ahead and get on the Cumberland map, or you can actually look it up on Google Maps.
Here's the
Also, I had a question. Could you updated the last time? It was at 8.22 out of 26. I think it's supposed to be out of 10.
Okay. Send me an email to remind me, because by the time I actually get a chance to get on.